So now we're going to take a look at this example as we actually try to find specific trig ratios based on the side lengths that are given to us in the diagram up above. So we're going to find the sine and the cosine and the tangent of both angle S and then also angle R. And we don't really have to find angle T. We could, but because that's a right angle, we'll talk about why that's not necessary later. But if I'm looking for the sine value, I'm thinking in terms of SO. The sine is the opposite over the hypotenuse. So I'm going to put the opposite here and the hypotenuse here. I'll do the same thing to make sure I'm thinking in terms of opposite in numerator, hypotenuse in the denominator. And let's just fill those in from that point. So if I'm keying in on angle S, the opposite side is going to be 60. And I know that this is my hypotenuse because it's across from the right triangle, so that's 65. So the ratio of the opposite over the hypotenuse based on it coming from angle S is 60 over 65, but I'd want to simplify that the best I can. So if I'm leaving it as a fraction, I could divide those by 5 and I would get 12 over 13. And more likely than not, we'd want to estimate that or approximate that by putting it into a calculator, and we would get 0.9231. We would do the same thing if we were dealing with angle R, but because we're coming from a different angle, that changes what the opposite side actually is. So here's angle R, and if I go across from angle R, my opposite side now is 25. The hypotenuse doesn't change because that's always going to remain across from the right triangle or right angle. So that's still 65, and now if I simplify that by dividing out 5, I would get 5 over 13. And again, we're probably going to take an approximation of that, 0.3846. Okay, so that's the ratio of the opposite over the hypotenuse. Okay, so we would say that the sine of angle S is 0.9231. The sine of angle R is 0.3846. Let's talk about cosine for a little bit. Okay, so the cosine we said was ka, so ka toa. Cosine is adjacent over the hypotenuse. I'm going to plug those in just to make sure that we can keep in track what should go as our numerator and what's our denominator. So let's again look at angle S, and I'm going to mark it up here in the diagram just to make sure I'm keeping it straight. And if I look at the opposite side, it's going to be over here. I don't want the opposite, I want the adjacent, so the one that's coming right off of the angle is 25. And the hypotenuse, of course, is the 65 that we've talked about. When I simplify that, I get 5 over 13, and the approximate value of that is 0.3846. That should sound familiar. I'll talk about that in a second. If I look at angle R, which is down here, the opposite side is 25. Again, I don't want that side. I want the side that's next to the angle, so that's 60. That's my adjacent side. 60 over the hypotenuse of 65 simplifies down to 12 over 13, which is 0.9231. That should also sound familiar. Okay, we've got the sine from that angle is the same as the cosine of the other one, and the cosine of that angle is the same as the sine of the other one. That is not a coincidence. That always happens in this right triangle trigonometry. Okay, so besides the right triangle or right angle itself, you have these two other angles, and the sine from one is the same as the cosine of the other. The cosine of one is the same as the sine of the other. Okay, so now let's find our last trig ratio. This one we call tangent. And remember, tangent is toa, T-O-A, so ka toa. The tangent is the opposite over the adjacent. So I'll mark that as opposite in the numerator and adjacent in the denominator. I'll do the same thing over here right away too. Okay, so let's start with angle S. If that's my angle that I'm keying in on to try to find this ratio, I'm going to talk about the opposite side, which is 60, and the adjacent side, which is 25. And when I simplify that, I get 12/5, which is the same as 2.4. When I look at the other angle, which is angle R, if that's the angle, now my opposite side is going to be 25, and my adjacent side is going to be 60. So basically the same thing except for flipped, right? Not 60 25ths, but 25 60ths. And therefore, when I simplify, I get 5/12, which ends up being about 0.4167. So that's the basics of how I go about finding these three different types of trig ratios. It's really just a matter of identifying which side is which. Is the side the opposite or the adjacent or the hypotenuse based on which angle that I'm keying in on. The last thing from this section that I want to show you is called the angle of elevation or angle of depression. And so you've got something that looks kind of like this. If you're looking up at an object like this guy is here, the angle that's formed between the line of sight and a horizontal line, so this angle, is considered to be the angle of elevation. And just the opposite, if you're looking down at an object like this girl is, the angle that's made up of your line of sight and a horizontal line is called the angle of depression. And so these two types of angles, angles of elevation and angles of depression, can also be factored in to what we're talking about with trig ratios. And you can see that here. Okay, so for example, let's do just a basic problem on the left that doesn't really involve that, and then we'll talk about the angle of depression that we see in the problem on the right. So let's first of all just work through this problem over here where we're trying to solve for x. And the way we do that is by saying we want to know what the tangent of 32 degrees is. Well, here's my angle of 32 degrees, and I have really two lines within that triangle that I know of. This one would be considered the opposite because it's across from that angle, and this one would be the adjacent. I can mark those. I think that helps. Opposite, adjacent here. What I'm really not using is the hypotenuse. Right? So now I'm thinking back to SO, CA, TOA, and which one of those three uses opposite O and adjacent A? That's the only one that uses it, right? This is O and H, this is A and H. I don't want those. I want O and A, opposite and adjacent. And that's why I know I'm going to be using the tangent value here of 32, not the sine or the cosine. Okay, so the tangent of 32 is TOA, opposite over adjacent, which is opposite of 11 and adjacent of x. Okay, so if I was to rewrite all of that, tangent of 32 degrees is x over 11. And so now I can actually use this to solve for x. I'm going to take x and multiply it on both sides. I'll multiply it over here and multiply it over here. The reason I'm doing that is just to get it out of the denominator on this side. So on this side I now have x times the tangent of 32 degrees. That's equal to 11. And now I can divide away the tangent of 32 degrees, because remember that's an actual value on that side, and I'm going to have to do the same thing on this side, the tangent of 32 degrees. Those cancel and I'm left with just x. So x is 11 divided by the tangent of 32 degrees. Now from that point, what you would do is actually plug in tangent of 32 degrees in your calculator. You could actually set that up and solve for it, or look in a big grid that has all these different tangents listed out. But tangent of 32 is an actual value, which is about 0.6249. And so when you take 11 divided by 0.6249, you find out that x ends up being about 17.6. Okay, so that's how you will work through this. I want to show you how that is done in the same way using this angle of depression, which happens to be a 21 degree angle. Okay, that angle of depression is part of really this horizontal line, this line of sight, and then a vertical line that connects the two. So you've got this triangle there with certain sides that are being shown to you. The reason we're using sine is, again, thinking through which values you have from SO and CA and TOA. And from this angle here, I have the hypotenuse of that right triangle, which is not included in TOA, and I have the opposite side, which is not included in cosine. Okay, so the things that I have are the opposite side and the hypotenuse, which means I'm going to use the sine value as part of my calculations here to solve for a missing value. Okay, so let's set that up. What is the sine of 21? Well, the sine, remember, is the opposite over hypotenuse, which is opposite 1200, and a hypotenuse here of x. So I'll rewrite that so we can just kind of get rid of that. That was just to guide me. The sine of 21 degrees is 1200 over x. And now I'm going to get x by itself in the same way I did on the left-hand side. I'm going to multiply it on both sides. That gets it out of the denominator here. So now I've got x times the sine of 21 degrees is 1200. Remember, sine of 21 degrees is a specific value. It's a ratio that holds true for every right triangle that has a 21 degree angle in it. Okay, so I'm going to divide both sides by sine of 21, that specific value. And if I do it on one side, I need to do it on the other side. Okay, that'll cancel out here. I'm left with x equals 1200 divided by the sine of 21 degrees. So what in the world's the sine of 21 degrees? You don't really have to know specifically what it is, because you can just plug it into your calculator and it'll spit out that value for you. It ends up being a value of about, what did I have, 0.3584 roughly. Okay, so when you take that 1200 and divide it by the sine of 21, which is about 0.3584, you get a value of 3,348.2. And so we use that trig ratio in order to solve for the distance that skier would go down, because that's really the hypotenuse of that right triangle.